Hi, my name is Laura Hanna, and I'll be presenting my work on the integration of unmanned aerial systems monitoring in structurally diverse forests. So, a couple different factors served as the motivation for this research. The first of which is the need for more frequent, widespread monitoring. Due to climate change, unprecedented disturbances, urban expansion, etc., our forests are rapidly changing. And in response, adaptive management practices and expansive monitoring programs have become more commonplace in forestry. A lot of these monitoring efforts consist of getting some boots on the ground and establishing plots where we can collect fine-scale data but can't necessarily cover a lot of ground, while others will use remote sensing via satellite where we can monitor large extents but sacrifice a lot in terms of resolution. So there's a lot of potential for unmanned aerial systems, or UAS, to kind of hit the sweet spot between these two methods. They can cover a lot of ground pretty quickly and collect relatively fine-scale data. At the same time, we're seeing a shift in a lot of forest management and forest restoration objectives towards promoting vertical and horizontal heterogeneity, particularly in historically heterogeneous disturbance-driven forests like low-elevation ponderosa. To adequately assess and monitor these kind of projects, we need to be able to collect more spatially explicit data, which UAS are ideal for. Although when it comes to collecting data with UAS in these complex heterogeneous forests, we tend to anticipate some amount of error. We generally know that things like variable crown cover and spatial aggregation can impede our ability to collect accurate data, but we don't necessarily know the extent of that impact. Which brings me to my research questions. First, how well can we detect broad spatial structures using UAS-derived structure from motion? Particularly, how well can we detect and analyze individual trees, clusters, and openings within a stand? And then, how does local forest structure, like local density or local height variability, impact our ability to collect accurate fine-scale data, individual tree data? To tackle these questions, we were fortunate enough to be provided with STEM maps of 14 ponderosa plots in the Black Hills. They received a variety of treatments resulting in a wide range of forest structures, but for the sake of this presentation, I'm just going to focus on the 3 plots pictured to the right to give you guys an idea of the range of structure across these plots. So starting from the top there, I'll refer back to these plots as high, mid, and low complexity plots. So using a DJI Phantom 4, we flew a crosshatch pattern at 80 meters altitude and collected images with 85% overlap. We then stitched those images together and generated point clouds using Agisoft Metashape. From there, we then extracted forest metrics from those point clouds in R. However, we weren't always able to pull DBH directly from those point clouds, so we also used regional FIA data to create a model to predict those missing values. We then took all of that and matched it onto our STEM maps for validation. To address broad spatial structures in the stand, we decided to identify individuals, clusters, and openings in each plot, and then compare the results between our STEM maps and UAS output. We defined individuals as any tree without the potential for interlocking crown. We found that the crown radius of overstory trees in the stand fell around 3 meters, so to be classified as an individual, stems had to be at least 6 meters away from any other stems. We identified these individuals, and then we took account of the numbers of individuals in each plot. Comparing our UAS data to the STEM maps, we found that it underestimated the number of individuals in the mid and high complexity plots. These missing trees were mostly small trees, those less than about 2.5 meters in height, that were entirely omitted from the data set. The drone just didn't detect them. But then we found that individuals were overestimated in the low complexity plot, and we decided to look into that a little bit further. So here we have our STEM-mapped individuals in blue versus the UAS-derived individuals in red from our low complexity plot. You can see that a couple of the extra individuals appeared possibly due to edge effects along the northern edge, most likely due to some small error in plot delineation. Some other trees in the middle of the plot were near small trees on the STEM map, but those smaller trees ended up being omitted from the UAS data, leaving those individuals alone. But there was also quite a bit of locational error on this plot in particular. While some of it may have been from the data acquisition itself, this plot also had the most mature trees of our 3 plots. And while tree locations on the STEM map were derived from the stems, the UAS tree locations were derived from treetops. So it's quite likely that any amount of tree lean could have been enough to alter our results, especially in these larger trees. So moving forward, it's worth considering developing methods to correct for this kind of error. But moving on to clusters, we essentially just took the opposite approach from what we took for the individuals. We defined clusters as a group of 3 or more trees with the potential for interlocking crown, so trees within 6 meters of each other. And from there, we used dbScan, a density-based spatial clustering approach, to identify and delineate clusters. Once again, we got a count of the number of clusters identified in each plot. Looking at these counts, we can see that our high complexity plot, the most aggregated one, was spot on. But the other two slightly overestimated, once again due to some error along the edge, or in the case of our low complexity plot, the commission of some trees, or false positives. We then took a look at cluster sizes in each plot, and we can see that UAS in blue underestimated the cluster size in our high complexity plot, where tree omission was more common, whereas it mostly overestimated cluster size in our mid to low complexity plots, where commission was more common. Nonetheless, the general distribution of cluster sizes was still relatively similar to that from the STEM map. Finally, to assess the inner spaces and openings in the stand, we created a distance matrix between trees, and then calculated the total plot area that fell at various distances from the stems. We plotted the UAS-derived distance matrix in blue against the STEM map in red, and found that they matched quite nicely, except perhaps the mid-complexity plot, which did have some commission error. In addition to the location of trees, we're also able to detect and delineate crowns. Although my previous analyses were based on the point density of stems, a lot of folks like to define individuals and clusters based on the current presence or lack of interlocking crowns. So it is worth noting that you can conduct similar analyses with crown polygons. You can take these polygons and dissolve them to identify individual and interlocking crowns, or buffer them to create a distance matrix to analyze interspaces. This approach is potentially more informative for forest managers, especially with regular monitoring. However, I didn't pursue this because it's really difficult to validate. Although it's relatively common for forest inventories to measure percent cover or crown width, it really isn't possible to adequately delineate or capture the irregular shape of crowns from the ground. So, for the most part, UAS can adequately capture and describe spatial structures throughout a stand. But how does stand structure impact our ability to extract individual tree metrics? To assess this, we derived some local structure metrics from the STEM maps using a 5-meter radius neighborhood. Specifically, we derived local density, both basal area per acre and trees per acre, as well as variance in tree height. We then took the UAS detected trees and matched them with the STEM maps to collect percent error in both our tree heights and DBHs. And then we plotted those error values against our local metrics. When it came to our tree heights, we had very little error, which was to be expected since the line of sight for treetops is generally pretty clear. So as a result, we really don't see any strong associations between our local structure and error in heights. But for our diameters, on the other hand, we began to see some trends. Across the board, we saw more error. Although there does appear to be a particularly strong association between trees per acre and error, likely due to the aggregation of small trees. And although there wasn't necessarily a clear association for our other metrics, we can still see that error becomes more variable as basal area and height variability increase. And while we can see these general trends, I recognize that there's still a lot of work to do here. So moving forward, we intend to refine this data to the point where we can perform significance tests to determine just how important these local structures are. And we'd also like to test more metrics. It's quite likely that crown cover or even the height of every individual tree would have an impact on data accuracy, so we'd like to test that. We'll also test the relationship between our metrics and commission and omission rates. Concerning future research, we should try to develop an improved model for DBH predictions, perhaps one that integrates soil type or site index. We should also test the efficacy of different sensors. Structure from motion is a relatively accessible form of UAS data acquisition, but it's quite likely that other methods may prove to be more effective. And finally, it's quite clear that most of the error that we see in our data was from tree diameters or missing tree stems. That being the case, it may be possible to accurately obtain that data through terrestrial structure from motion. Developing methodology to combine aerial and terrestrial structure from motion could be incredibly useful for evaluating high-value timber or quickly and accurately creating stem maps. And on that note, thank you for tuning in, and feel free to reach out to me with any questions.